Oh, it's a beautiful day today. Look at those clouds. They're not over sky here, but I'm hiding out in the shade as some folks are hiding out in the castle, and I'm here ready for our next science note page about activation energy and catalysts. So let's jump in. Let's do this. Our last science notebook page of the Black Diamond unit. All right. Well, activation energy and catalyst are two vocabulary terms that we're going to draw some pictures for and define on this page. So make sure that you have room for both of them here. It should just take one page. So this idea of activation energy. Activation energy is the energy that is required for activation to occur. So think about if you're trying to get off of the couch, you're trying to activate to go do your chores. Sometimes it takes a lot of energy. Other times it doesn't take much energy. And sometimes your parents say something that adds a little bit of extra energy, like if you do it in the next 5 minutes, I'll give you $1 million. So keeping that in the back of your mind, let's talk about activation energy and catalysts. Activation energy is the least possible amount of energy in a chemical system required for a reaction to take place. So it's the least amount of energy in a chemical reaction or in a chemical system, the least amount of energy that's required in order for that reaction to take place. So let's look at this as though we have our reactants. So we need to draw a line here for our reactants and then one for our products. And in order for the reactants to turn into the products, you can see that if this is the amount of energy that our reactants have, and this is the amount that our products have, we're going to lose energy in this system. And so it's actually going to release energy. And so this would be an example of one of those exothermic reactions because it's going to release energy into the environment. But in order for the reaction to happen, when the reactants are together, they don't just necessarily happen. Sometimes, like if you're in Antarctica, it'd be too cold for the reaction to happen very quickly. If you have more heat and you're in the tropics or something and it's warmer outside or warmer in your science lab, then sometimes it actually happens quicker. But the activation energy is basically like this hump of energy that's required. And you have to get up over this hump in order for the reaction to occur and for the products to form. So this would be an example right here of, we'll call this high activation energy. So it's a lot of activation energy. And what we're really measuring here is this distance of how big is this kind of maximum of the graph here. This is the activation energy. Okay, let's look at the opposite here. Let's look at something that would be considered low activation energy. Low activation energy might be something that has a very small little bump, and so the activation energy would be much smaller compared to the other one because it doesn't take as much energy to go up over this little bump here for that reaction to proceed to the products. So there's some things that they would react out in nature, but they don't because there's not enough energy in the system to cause the reactants to turn into the products. So an example of this is the hydrogen peroxide. So the hydrogen peroxide is an example that we used in class when we made the elephant toothpaste. And when we made the elephant toothpaste, it released a lot of oxygen. But when you just have hydrogen peroxide sitting on the counter, this doesn't happen. So in order to get it up over this hump, we had to add something called a catalyst. And in the example of elephant toothpaste, the catalyst was actually the yeast. So let's define what a catalyst is. A catalyst is a substance that speeds up a chemical reaction It's a substance that speeds up a chemical reaction without being consumed in the reaction. So we added the yeast, and it was not actually consumed by the hydrogen peroxide, but it gave that extra encouragement to speed up the reaction. So if we were to draw the activation energy, let's say that it takes a lot of activation energy to get the hydrogen peroxide to turn into oxygen and water. So we'd say that's a high activation energy. But when we add a catalyst, Let's see what happens. So we have the reactants plus our catalyst here, and it actually causes the activation energy to be reduced. So usually there's the high activation energy, but when you add a catalyst, it provides a new pathway. It says, oh, well, look, if you want, you can go this way, and this doesn't take as much activation energy. So catalyst provides this alternate route that allows the reaction to speed up and go this way to the products, so it happens much faster. In the elephant toothpaste, it happened really fast, and it created all of that glorious elephant toothpaste. So if we go back to my original example, sometimes it takes a lot of activation energy to get off the couch and do your chores. But then your parents say, remember, it takes a lot of energy, but your parents say, what about $1 million? And you're like, yeah, woohoo, let me go do my chores. And you go do your chores, and then you're a millionaire. So one last thing to add to our page. Catalysts provide alternate paths for the reaction. An alternate path for the reaction, which requires less activation energy. And that's a catalyst. So catalysts really, really help out, and they're all over the place out there in this world. So keep your eye out, be a good scientist, look for those catalysts. See ya.